Hello everyone, welcome back to the discussion. It's a great pleasure to back to you with the discussion on new interesting topic, and today we shall discuss about some interesting topic, and it is about quantum mechanics. So at first we shall have to know the fundamentals of quantum mechanics. So in order to do that, at first allow me to do some discussion on the classical mechanics. So at first talk a little about classical mechanics. Classical mechanics. And you all know in classical mechanics all the systems are categorized in two distinct category. So in classical mechanics all systems in this universe are categorized in two distinct category, and the first category is called matter system. It is matter system, and the second category it is wave, or you may call it radiation, wave or radiation. So in classical mechanics all the systems have two different category. One is matter system and another is wave system or radiation system. And you all know what is the distinction between these two different system. And you all know for matter system, that means matter system has particular position and momentum at any particular instant of time. So it has particular position like x and momentum at any time t. So let me denote it like xi and phi at any particular time instant ti. So matter system has a particular xi and particular pi at any instant of time ti. But for wave system, you all know what is wave. Wave is such a system which has no particular position or particular momentum at any particular instant of time, because wave is spread everywhere in space. And you may realize that suppose you all have mobile receiver, and the signal coming from the network tower will spread everywhere, and where there is some mobile receiver, the mobile receiver can track this radiation. So suppose any source of wave is here, so it may spread in all direction through the space, and where there is detector, the detector can detect this wave at any point on space. So wave has no particular position and particular momentum at any particular instant of time, because as like position, wave may possess continuous energy. So as energy is continuous, so it must possess the indefinite magnitude or indefinite values of momentum at any particular instant of time. So for matter system, it possesses particular position and momentum at particular instant of time. But for wave or radiation, it does not show such type of property. So it is the clear distinction between matter and wave. Now let me discuss it in some details. Like, so at first we shall talk about the matter system, and you all know to analyze the dynamics or realize the dynamics of any matter system, that means to access all the dynamical observables or all the dynamical variables of a matter system, we generally apply the Newton's laws of motion. That means for matter system we generally apply Newton's laws of motion, to realize the dynamics of any matter system. That means to access or to obtain all the dynamical observable, like the dynamical observables of a matter like position, momentum, that means other dynamical observables like energy, velocity, etc., etc. Such type of dynamical observables can denote this system, or can represent the dynamics of that system, and one may access all these dynamical variables through Newton's laws of motion. Or not only that, many may say that they can apply Lagrangian mechanics, or they can apply Hamiltonian formulation, or other advanced methodology to access these dynamical variables. But let me remind you that such type of advanced methodology, that means Lagrangian formulation, Hamiltonian formulation, or D'Alembert principle, or the advanced methodology like Hamiltonian Jacobi equation, such type of advanced algebra is the modification of Newton's law. So the basic ideas or basic mathematical tools to access all the dynamical observables of a matter is the Newton's laws of motion. So at first, talk about the simplest matter system, and you all know that the simplest matter system is nothing but a point particle. So a point particle is the simplest matter system, and we may apply Newton's laws of motion to realize the dynamics of a point particles with mass. So it's a point particle with mass, a point particle of mass small n. Now let this small point particle with mass m moves in a constant acceleration. So applying the Newton's second law of motion, one can write that the force is equal to m multiplied by a, where a is the acceleration of the particle. So it's a very simple thing, you all know, and you all know about this equation from your secondary level or before that. And then we may write that mx double dot is equal to ma, which is x double dot is the second order derivative of position with respect to time. And then one can easily write x double dot is equal to a, where a is the acceleration, and here we can consider that a is a constant because the particle moves under constant acceleration. So x double dot is equal to a. Then this differential equation can be solved easily just by integration on both sides. One may find x dot is equal to at plus c1, where c1 is the integration constant. Then further integrating on both sides, one can find x is equal to half of at square plus c1t plus c2. So that is the expression of position as a function of time, and x function of t is equal to I am writing it further, half of at square plus c1t plus c2. So through the mathematical tools of Newton's laws of motion, that means this equation F equals to ma, one can easily find or obtains the position as a function of time. That means xt is equal to half of at square plus c1t plus c2. And the beauty of this equation is that one can find the position of that particular system at any future and past instant of time if the time is given. That means if I am said to find the position after 1 crore year since now, then I can put here the value of t 1 crore, then I can find the value of xt at that instant of time. And similarly, not only the position, we can find the velocity also, because the expression of velocity is nothing but the first order derivative of x with respect to time. That means nothing but x dot is equal to at plus c1. So here, if the value of t is given, that means if one tries to find the velocity of that system at any time instant like t1, then he can easily, or one can easily find the value of x dot or velocity at that instant of time. And hence not only the position or the velocity or the momentum, one can easily find all the dynamical observables at any future or past instant of time by applying the Newton's laws of motion. So it's a beautiful tools, and it's a very effective tools to find the dynamics of any system. But still here there is a important issue, because it is possible to find the all the dynamical observables associated with the dynamics of the system if the values of C1 and C2 are given. If the values of these two integration constant, that means the unknown integration constant, are given, then one may apply the Newtonian tools or Newton's laws of motion to find the dynamics of that system. And one can supply the values of C1 and C2 by some boundary conditions or initial boundary conditions. And the boundary conditions may be supplied that any particular instant of time t0, let at t equals to t0, the value of position is suppose x0. And similarly, the value of the velocity of the system x dot is equal to v0. That means if such type of boundary conditions, there is two boundary conditions, that means the value of position and the value of velocity at any particular instant of time are supplied for a, or supplied or given for a particular system or particular matter system, then one can find this integration constant C1 C2. And because putting these boundary conditions on in this equation, one can find the value of C1, and just putting this boundary condition in this equation, one can find the value of C2. Hence C1 and C2 can be obtained. So it is clear that if such any boundary conditions like the value of position and value of velocity are given at a particular instant of time, then one can easily use the Newtonian tools to find all the dynamical observables of any system at any particular instant of time deterministically. So it is a deterministic mechanics, because if such type of boundary conditions are given, then the system can be obtained deterministically. So it is a deterministic mechanics. But there is another issue. Let me repeat this expression, that the boundary conditions like at t equals to t naught or t0, x is equal to x0, that means positions are given, and also the value of x dot, that means x dot is equal to v0 is given. But one may supply the boundary conditions in the form that the momentum of this system at t equals to t0 is equal to p0. So it is clear that if we want to find or access this system, then we have to supply this pair, the values of this pair, which is the values of this pair x0 and p0. So x0 and p0 is the way of representation of the system, or the way of representation of any matter system in classical mechanics. But here is another beauty, and the beauty is these boundary conditions, or these two boundary conditions, may not be unique, because any system evolved with time may show different values of x and p at different instant of time, and all the values of this pair at different instant of times are equally able to represent that system, because x and p, that means suppose I have represented the system like that at t equals to t0, x equal to x0 and p equals to p0, but another person may represent this system like at t equals to t1, x equal to x1 and p equals to p1. Similarly, other person or third person from these two person may represent this same system in the way that at t equals to t2, x is equal to x2 and p is equal to p2, and there are many that means the infinite number of boundary conditions can be applied for the same system, and all the boundary conditions are equally correct and equally applicable to represent the system. And hence, if we reduce the partiality, so we can do some trick to represent the system in a unique way. That means if we make a plot between the position and momentum of the system, then we can find some plot like that, and each point on this plot supplies the values of pair xp, and all the xp are equally able or equally correct to represent this particular system. And such type of plots between the position and momentum of any system is called the phase space of the system. So in classical mechanics, any matter system can be represented by its phase space. So it is called the phase space. So any system in classical mechanics can be represented by its phase space. But for wave system, it is impossible to construct such phase space, because for wave system we cannot find some such type of graphs between p and x, that means between momentum as a function of position at any particular instant of time, at any particular shapes, because it has no particular values of p and x, so we cannot make such type of graphs. So in this way we cannot represent the wave system in classical mechanics. But in matter system, or in the case of matter system, one can represent that matter system by its phase space.